Hi everyone, we're now going to transition into trying to get a formal definition of continuity. I hope that you have a decent working definition of continuity. I would say a good pre-calc version of that is if you have to pick up your pencil to draw it, it's not continuous. I would add to that, we have some infinite oscillation in this picture, which doesn't come up much, but that would count as a discontinuity as well. You don't have to pick up your pencil, but you also can't even draw it accurately. So this is a preview activity to get you going on this thinking about how do we formally define continuity. So pause, try it out, and then watch really quick just to see how you did. Part A and B go together, and what we're supposed to do is go to each integer value and take the limit as x approaches that value. If the limit exists, we're also supposed to say if the value of the limit is the same as the y value right at that x coordinate. So the first one on our list is going to be the limit as x approaches -3 of f of x. And on our graph, here's -3. As we come in from the left, our y values approach 3. And as we come in from the right, they also approach 3. So it looks like that is 3. The limit as x approaches -2. There is a discontinuity at -2, so I'm seeing on the left side it approaches 2, on the right side it approaches -1, so that's a does not exist. The limit as x approaches -1 is maybe like -3.25, and then about -3.25 from the other side. Does not matter that there's an open circle there. We're asking what's happening nearby, so I'm going to say -3.25, and maybe we'll say approximated. The limit as x approaches 0 of f of x. So both sides are approaching what appears to be -4. The limit as x approaches +1. Looks like about -3.25 again, continuous there, so nothing weird happening. The limit as x approaches 2 looks nice as I come in from the left-hand side. It looks like I'm getting really close to -2.5, but then I think I'm seeing infinite oscillation, so that's going to be a does not exist. All right, last one. The limit as x approaches 3, f of x. There is an open circle. That should be fine for the limit. It looks like both sides approach that same open circle, so that will be -2.5. Okay, so those are the limits at every integer value. We now want to look at each of them and think about what the y value is and if it's the same. So f of -3 is 3. So that one is yes. We don't need to look at the does not exist. So let's skip to x approaches -1. F of -1 is 1. So that is not equal. The limit as x approaches 0 was -4. F of 0 is also -4. As x approaches 1, I scribbled on that, but I don't think there's anything too weird. Okay, so f of 1, it looks like it's about -3.25, which does match up with the limit. So that does equal f of 1. And then as x approaches 2 didn't exist, so we'll skip that one. F of 3 is undefined. You can say does not exist if you want to, same idea, but f of 3 is undefined, so it can't possibly be equal to the limit as x approaches 3. So the yeses are at -3, at 0, at 1, and I guess that's it. That's the only ones that agree. All right, this next one is just to summarize what we already said. So we want to know when the limit does not exist. So again, we're just looking at the integer coordinates. We're not worrying about everything in between. The limit did not exist when x was -2 and also when x was 2. Those were our bad limit points. At which values is f of a not defined? I think we only found one of those. There's some funny spots in the graph, but I believe x equals 3 was the only time that the function wasn't defined. There was no y value on that graph. At which values of a does f have a limit, but the limit is not equal to the y value? Okay, so that was this one. I think that's the only one I wrote down. So that was x equals -1. Okay, and then we want to look at all values where the function is not continuous. So this is where we can go back to our working definition. Our working definition says if you have to pick up your pencil, it's not continuous, and I'm adding infinite oscillation. So not continuous at -2, there's a jump. Not continuous at -1, there's a hole, and your point is up here on its own. Not continuous at 2, and not continuous at 3. So -2, -1, 2, and 3. All right, so what I want you to notice here is that this final list we got matches up with what we got when we answered these questions up above. So we have a problem with continuity if the limit does not exist. We have a problem with continuity if the function is undefined, and we have a problem with continuity if those are both defined, those both exist, but they're not the same. And this leads us to our formal definition of continuity. So here it is. We've always just gone with this kind of rough understanding. A function is continuous at x equals a if, and it's basically a checklist. 1, the limit as x approaches a of f of x exists. So if you get a does not exist, automatically not continuous as well. F of a also has to exist. And then the final check is that they're the same. So these ideas of continuity and limits are completely entwined with each other. We kind of can't talk about one without bringing up the other one, and that's why they're both in this section.